Hello, Calculus. We have a catch up from 214 to do, number 2 on those notes. We did 1 and 3 in class. And then 215 notes, a couple different examples throughout these related rates. So I just put this up here, 214, to remind you of the steps we're going to go through. We'll have, I think, 2 questions to answer for me as you go through this. So make sure you get those answered for your points. And make sure you can follow these notes. Let me know if you have questions. All right, the steps we went through with these related rates. Remember, rates are derivatives. That's change in variables compared to each other. So that's going to be a rate between variables. So what we're doing with the derivative on here is, first, we need an equation. So first thing was write an equation that relates the variables that are changing. So usually it's a geometry thing. We did Pythagorean theorem. There will be other area or volume formulas, and we'll see a couple others today that we're going to use. But the important part here was, as we draw a picture, usually helps us. Variables are places that really distances change. So if it's not changing, it's not a variable. Just leave a number there, and that makes it fewer variables to work with the derivative. Second, differentiate, take the derivative of with dt. Every variable gets this little fraction, dx dt, or dA dt, or dv dt, whatever it is. That variable represents how fast it's moving in that direction. So there's our rates in the problem. And then substitute known variables, or values. So we're going to plug in. All right, let's take a look at that problem we skipped over in the notes in class. Number 2 on the 214 notes. So the water is flowing into a tank, the shape of an inverted cone. I'm going to try to draw this as we talk about it. That just means, think of it this way. We're kind of filling an ice cream cone here. So I guess we're filling it with water. So we'll put a little water spigot up here. So turn it on and the water flows into the cone. At first there's a little bit of water. Fill it more. Water goes up in the cone. That's what we're doing. We're talking about how much water is in this tank. So water's flowing into the tank at a rate of 40 pi cubic centimeters per second. This cube is actually important for us to notice here to get the right equation. It tells us about the height of the tank and the radius of the tank. The whole thing is height of 80, radius of 160. I guess I drew mine a little bit too narrow. How fast is the water level changing when the water is 15 centimeters deep? Then another question we can answer after that. So let's think about what we need here. First, figure out the formula. I didn't tell you a formula on this one. You can write it down from what I give you here and use it for your notes. But this is water flowing into a tank, a 3-dimensional shape. We're filling 3 dimensions. That's volume. Or this is why the cube was important. You should know your units. Cubic units is always volume. So we are talking about volume of a cone. Now we're actually talking about the volume of water in the cone, how much water is in there. So, but that's still, it fills the cone. It makes a cone shape of water when it's inside the tank. So volume of a cone is, this is step 1, write the equation. V equals 1/3 pi r squared h, radius, height, volume. Okay, now if we look at this, let's see. We're talking about how much water is there. So it's just the water, not the entire tank. So as we fill the water in here, obviously more water, more volume, the volume changes. That's a variable. As we fill, we said it gets higher up in the cone. So the height is a variable. So 2 variables so far. The radius. Well, the higher we are, the larger the radius of water. So we fill it up more, bigger radius of the amount of water in this cone. So the radius is a variable. There are 3 variables in this. Now, there is a hard way and an easy way to do this problem. The hard way is just to take this and start doing its derivative. You have to do a product rule. You have 6 variables because we have 3 variables now and we will have 3 derivative variables. That's going to be harder. So we always want to make problems easier first. How can we make this easier? Well, fewer variables is easier. So we have to know about this cone. And you can see in kind of what I drew here, the height and radius idea. And if we draw on the side of the cone, what we've made are actually similar triangles. So we have a small triangle down here at the bottom of the cone. If we fill it up, we have a little bit bigger triangle that's similar. Well, if it's similar, that means the height and the radius are really related to each other. If I tell you the height, I bet you can tell me the radius. Okay. Now the whole thing is 160 radius, 80 height. That's a ratio we can use. If I tell you we're halfway up in this cone, well, that would be 40 for the height. We'd be halfway with the radius. If I know 40 is the height, 80 for the radius. So here's what we're going to do. We are going to substitute. Okay. We want fewer variables. Okay. If we can. And this one we can. So find out how the radius and height are related. What I see is that the radius is twice as big as the height. That will be the same ratio throughout this whole tank as we fill it. 160 and 80, twice as much. Now, or you could write it the other way. You could see that the height is half the radius. So we're going to use that to substitute in. So we don't have both of these, R and H. It's going to be easier with one variable. So they're going to tell you something. Here they told us the actual dimensions of the cone that's holding the water, so that's our ratio. They might just come out and tell you, the radius is 5 times the height. Well, then you can write your little equation. We're going to substitute that in. But since we have 2 different options here, look through the rest of the problem. It says how fast is water level changing? Water level is height, okay? When the water is 15 centimeters deep, that's a height. Depth and height, same thing. So I want to keep H. Means I replace R. So I'm going to replace my R. And that says R equals 2H. That's the one I'm going to use. So figure out which one you want to get rid of and replace with the other one. So now our equation would say V equals 1/3 pi. It's going to be R squared H, and the R is being replaced with 2H. Simplify, and we're going to be good to go on an easier derivative. So this is V equals 1/3 pi. Square both, so it's 4 times H squared times H. Make sure you square both parts in here. And combine those, and our final result is 4/3 pi. Remember, that's all just a number. H to the 3rd power. That's an easier equation to use. Fewer variables, it's going to be a lot better to do the derivative. So a cone problem, this is about the only one you have to do that on. Most formulas only have one variable on this side, either a radius or a height. This one has both. So volume of a cone, find a relation between radius and height, and make it easier first. Now we can do step 2. Derivatives should be easy for us. These all really turn out to be power rule problems for these formulas. So V, derivative is dV dt. Over here, remember, this is just a number, okay? 4/3 pi is just a number. If this was like 5 pi, or even just, 7h cubed, we'd just use a power rule. Multiply the 3 in front, subtract 1. So multiply the 3 in front. That makes it 4 pi h squared. We just did a power rule. That's all. So a power rule problem. Now we did just do a derivative, h, so it needs dh dt. That is our derivative. Step 2 should be a quick step. You just have to use the right rule for the derivative. And step 3, skipping ahead. Step 3 is plug in. We had a v variable and we had an h variable when we simplified. So now we have a dv dt and a dh dt. I keep track of these so I know which ones I'm plugging in, which one I'm solving for. And let's see what we have. They started us out with this number of 40 pi cubic centimeters per second. Remember, cubic was a volume, per second is a time, so that must be the dV/dt, volume per time, 40 pi. The height of the tank and the radius of the tank don't matter. That gave us the ratio. It doesn't tell us where the water is, so don't substitute those in. How fast is water level changing? That's the question. The water level is height, but changing, remember, is your rate word. So we are looking for the dH/dt. And when the water is already 15 centimeters deep, that's our height of the water. So 15, and it looks like we have one left. Remember, if you want an original variable, go to the original equation. But before you do that, let's wait for the bells at school here as I record. Before we do that, look at your derivative. There's no v. The v changed to dV/dt, so we actually don't even need that one. Okay, we could find it by plugging in 15, but you'd never have a place to plug it in. Okay, all right, so we don't need the v. Let's just go on. dV/dt is 40 pi equals 4 pi. H is 15 squared, and solve for dH/dt. Basically, we're going to divide by all this stuff over here. But you can clean it up first to make the division easier. Use your calculators too. But what I see here is there's a pi on both sides. Cross it out. Okay. Maybe just do one piece at a time. Divide by 4 first. So 10 equals, and 15 squared is 225 dH/dt. So take some steps to go through this. 225 divide by 225. So our dH/dt is 10 divided by 225. You could leave the fraction, you can reduce it. You can pull out your calculator and get it too. This is fine for a word problem. 3 decimal places, that's 0.444 on this one. Okay, so 5 goes into both of these, and you can reduce if you really want to. But we have not 0.444, 0.044. Make sure I get the right thing on my calculator. Always need units. So look at the dH/dt. The units for height, well, the only kind of measurement they gave us was centimeters in here. So height is centimeters. And then over time, the only time unit they gave us was seconds. So dH/dt is centimeters per second. So the water is rising at 0.44 centimeters per second when it's 15 centimeters deep. Okay, and a change if it's other centimeters deep. So that's the first question. Now the second question says on here, we don't have to do a lot of extra work. How fast is the radius of the water changing at that time? So how fast is it spreading out in the cone? Well, for that one, we do not need to go back and do the problem again with a radius. So for the second problem here, take a look at what we know. We know dH/dt, and we know that radius is twice the height. Well, I want to know how fast the radius is changing. Means I want to know a dr/dt, the radius change. We'll use this simple equation. If r equals 2h, then dr/dt equals 2 dH/dt. And we can plug in there. So dr/dt is just twice as much as this 0.044 that we just found. So you don't have to go back and do the whole problem again. These two are related. The height and the radius are related in a simple ratio. So their derivatives are related in that ratio. So 0.088. And that is in centimeters per second as well. Okay, that's the idea for a cone. Let's keep going with now on to a couple other types of problems on 215. First one. So we've done some geometry stuff. This one, we have a word in here that will tell us how we need to think about this problem. But let's look at it the same way. Kind of come up with a picture first and what kind of geometry. Dog is 16 feet away from the tree, watching the squirrel climb up the tree. Good dog, he's just sitting where he is. Here's our dog. Okay, there's the dog. Tree over here. There's our tree. We've got a squirrel climbing up the tree. Okay, and our dog is just watching that squirrel go. There's our squirrel. So what kind of situation do we have here? Well, we have the dog is away from the tree. The squirrel is going up the tree, and the dog is looking at the squirrel. There's a triangle in this one. This is a right triangle problem. Um, right now, if we don't read on, we might think Pythagorean theorem because we have distances. The dog is 16 feet away. Good, dog, he's not moving. That's not a variable, it's just 16. Squirrel goes up the tree. That distance changes. So that's a variable. Let's put a y on there for a vertical. You can use whatever you want. And the distance between the dog. Well, that could be a variable because that's going to change depending on how far he is up the tree. Okay. But read on. Okay. It says, how is the dog's angle? Angle of elevation. Looking at the squirrel changing. We need an angle in here. Remember, the angle of elevation talks about right here. How fast is the dog having to look up? Okay. To turn his head up. We need to know about this angle. This is no longer Pythagorean theorem. So the angle means as soon as you see that word, we have to do trigonometry on this one. Okay? So we have to pick a trig equation that will help us on this. Now there's different options to use. We're just going to go back to SOHCAHTOA and plan this out. And you get to pick the best trig equation that you can find. Now really, look at what you know most about. Okay? We could think of sine, cosine, and tangent on this one. But as I read through here, I'm going to mark down exactly what we know here. We know the dog is 16 feet from the tree. They describe that side. With our angle, that's the adjacent side. We know the squirrel is climbing up the tree, and later on they tell us it's a rate. Okay, so they tell us about y. That's the opposite side. Those are the two sides I want to use, especially because the 16 is not a variable. It's fewer variables are better. They don't tell us anything about the distance here on z, so I don't need that. So I'm going to look at what they're describing. So they're describing the opposite and adjacent sides. That is tangent. Tangent of theta, there's one variable, equals y over 16. There's one more. Two variables is good. Okay, I'd like not to have three. So this is good. Trig tangent theta is y over 16. There, it's step one. That word angle in there tells you about trig. Okay, so step two, do its derivative. Trig, derivative, tangent is secant squared. Secant squared theta, theta gets a d theta dt. You can use x as your angle if you really want to, okay? Y over 16 derivative. Remember, y over 16 is the same as 1/16 y. That's just a coefficient. So this is just 1/16. But it's a y, so it gets times dy dt. Okay? So not too hard on that derivative. You know your trig derivatives. Just do the little d theta dt and dy dt when you do those. Step two should always go pretty quickly, even though that's the calculus step. Now, step three, let's look at our variables, and there's a change on trigonometry. We had a theta, and we had a y. We have a d theta dt, and we have a dy dt. Okay? So, as we look at this, first, kind of like one of the last questions, look through here. Look at your variables. Make sure you have them. We have a theta. Keep it. We have a d theta dt. We have a dy dt. There's no y. We don't even need to know y. Okay? So now we're down to three variables. Plug in two, solve the other one. And let's see. 16 feet we already used. Read through. 6 feet per second. That is the rate of climbing. So that is the dy dt. How is the angle changing? So we're trying to find the theta dt. That's the one that's missing, the angle changing. When the squirrel is 12 feet up the tree, the 12 is the y. Okay, didn't have to look too hard for that. We're missing theta. Here's the secret of trig. On all these problems I give you, you do not need your calculator. Usually we said if you need an original angle, look at the original equation. Plug 12 in, do an inverse on your calculator and you can get the angle. You don't need to do that. Here's the trick with trig. Don't think of theta as your variable. Include its trig function. So our variable is actually secant of theta. Why do we do that? Well, we did that because we can find secant of theta without our calculator. We're just going to use SOHCAHTOA. The triangle that we have over here, pieces are moving, but at this time, what we know is 16 is we said the adjacent. The squirrel is 12. That's the opposite. We can find the hypotenuse. This is really a 3, 4, 5 triangle, so that's going to be 20. Okay, 12, 16, 20. And you can give me the secant. Secant of theta is, what's the reciprocal of cosine? So that'd be hypotenuse over adjacent, or 5/4. If you think of the trig function, you can plan a SOHCAHTOA fraction right there. You do not need to find that angle on your calculator. So that's the secret to trig. So the trig is your variable, or is your variable you're going to plug in for. Secant of theta, not just theta. Well, let's plug in. That means secant squared is going to be 5/4 squared times d theta dt equals 1 over 16 times dy dt is 6. Okay. 5/4 squared is 25 over 4. D theta dt, that's a lot better than using fractions and angles and everything on your calculator. 6 over 16 is 3/8. To solve for d theta dt, I'll use the reciprocal times 4/25. Okay. Reduce a little bit, we could reduce that. We end up with 3/50 on this one, it looks like. Make sure I get the right thing. 6 over 16. I didn't square the 4. 16 down there. 16 up here. So we actually get 6/25. I knew something was weird about that answer. 6/25. Okay. If you want to put in the decimal, you can. But d theta dt is, what is that going to be, 0.24 or something? So 6/25. Now we need a unit. I know it's going to be per second because that's the time. dt. What is theta measured in? You never found an angle on this. They didn't tell you degrees. They didn't tell you radians. Didn't tell you anything. The answer to this one is radians. Now, it's kind of a complicated answer, but basically, we're in calculus. We're using radians. But radians, remember the definition, is based on length. It's an arc length. So radians is what we're using to relate to lengths around this triangle. Degrees is made up. Okay, degrees is astronomy. It's days around the sun. So radians is what we will always get to because this has to do with a ratio of lengths. So that's why it's radians. There's our answer. So secrets to trig. Angle means you're doing trig, and when you think of the variables, think of the trig function as your variable and build a triangle to use SOHCAHTOA with, and you have a number to plug in. Okay. Last one here, last kind of option. This one was not one we did last year. We had done some trig last year in pre-calculus. This one, we did not. So this one actually, maybe we have to go back a little bit more to remember how to set it up. But the calculus actually ends up pretty easy, as long as we get the right situation here. Boy is walking away from a street light, and we know how fast he's walking. How is the shadow growing? This is a shadow problem here. Let's look at this situation. We have this street light over here, okay? So here is our street light shining down. We have a boy walking away from it. Nice little 4 feet tall. Don't have to use decimals here. So as the light shines, that creates the boy's shadow down here. There's the boy's shadow. Depending on how far he is away, longer or shorter shadow is what we have. Well, what situation in geometry do we have here? We have a boy in the light post. Here's the ground. We have this line going out. What we just have is similar triangles. So this kind of shadow problem is similar triangles. That means we are going to write a ratio of sides. That's how you did similar triangles back in geometry. So how do we write the ratio of sides? Well, let's look at variables on here first. The streetlight is 10 feet tall. It's not changing. Those don't grow. The boy is 4 feet tall. He's not changing. Boys don't grow. Well, not that fast. So he's going to still be 4 feet tall as he walks away. Let's see. The distance from the streetlight. That is changing. The boy is walking away. So that's a variable. Let's just put X. And the shadow, that's a different length. And depending on how far he is, that changes. You get farther from a light, your shadow gets longer. So that's a variable. Those are the only ones we need. So that's how we're going to set up this type of problem. The ratio is, you can write it a couple of different ways, but you might remember doing corresponding sides, like 10 on the big triangle, the street light, 4 for the boy. Those are parallel sides. Those are on the vertical side. The other one would be this bottom side, and that one's a little bit trickier. The full triangle is down here. So the full side of that triangle is x plus y. This is x plus y over the little triangle is y. Now we could write it a different way. We could do the light post, and that would be 10, and the full bottom is x plus y. And then the boy ratio is height is 4, the bottom length or horizontal length is y. Either way is fine because of the next step. Simplify first. But that is our ratios. Okay, we're not done. We're going to simplify for step 1. When we simplify, we cross multiply, and both of these cross multiply to be 10y equals 4x plus 4y. Well, let's make it easier. Subtract the 4. 6y equals 4x. That is step 1. That's an easy equation. So these shadow problems do come out to be an easy equation. We just have to remember how to do ratios of sides to get there. Let's go to step 2. Step 2 is going to be find the derivative. Well, 6y, that's just going to be 6 and dy dt. 4 dx dt on the other side. Nice, easy derivatives to do. When we're done with that, let's plug in. Step 3. Oh, we had a y, we had an x. Now we have a dy dt and a dx dt. Well, look at our derivative. There's no more y, there's no more x. We don't need them. So we only really need one variable to plug in, and the other variable we'll find. So let's see. The boy is walking away at a rate of 2 feet per second. When he's walking away, he's changing the x distance by 2 feet per second. So that is dx dt. If you look, y is the length of the shadow. So dy dt is how fast the shadow length changes, and that is what they're asking us. How fast the boy's shadow growing, that's all derivative stuff about the shadow. So dy dt is the one we want to find. So 6 dy dt equals 4 times 2. So dy dt equals 8 divided by 6 equals 4/3, 1.3 repeating if you want, and y is measured in feet, and seconds is the unit. So 4/3 feet per second is how fast his shadow is getting longer from his feet to the tip. Okay, that's the first. And then they ask us a second question. Let's see, part B. How fast is the tip of the boy's shadow moving? Well, the shadow is getting taller at 4/3 feet per second, but that's from the boy's feet to the tip. The boy's feet are moving away. So if we look at the tip of the shadow, it's moving extra fast, more than just this 4/3. The boy's not just standing there. So as the boy moves, the tip moves and it gets longer. So this one, we don't have to do a lot of extra work. So the tip of the boy's shadow would include both the x and the y. What we're looking for is the distance from a fixed object, which is the light post, to the tip of the shadow is x plus y. So its rate is going to be the derivative of x plus y dt. Now, how do we do the derivative of two things together? We do them separately. This is going to be dx dt plus dy dt. So what we're saying is the shadow is getting bigger at 4/3 feet per second. Well, the dx dt, the boy's walking at 2. So it's going to add 2. 2 is the speed that you look at that tip of the shadow moving along the ground. So 2 and 4/3, that's not good. 2 and 4/3, that's going to be 10/3. That's the better way to write it, and that is in feet per second. So the tip of the shadow is moving at the rate that he's walking plus how it's getting longer at that time. So that is the idea for the shadow problems. All right, use that to try problems on your homeworks. Email me questions. I can put together some help with some of those problems, and we'll be talking about that the next time I see you, a lot of these questions. Okay? All right, good luck with all those, and I will see you next time.